everyone, welcome to our third and final video on double integrals over rectangles. And in this video, we're going to focus on more complicated iterated integrals. Recall from our last video that Fubini's theorem told us that if we have a continuous function f on our rectangle R, then in theory it does not matter the order we choose to integrate with. So we can integrate first with respect to y and then with respect to x, or first with respect to x and then with respect to y, and Fubini's theorem says that as long as our function is continuous on R, then we will get the same answer. However, the goal of this video is to show you that while in theory it may not matter the order that we choose, in practice we may want to think about which order we integrate in order to make life easier on ourselves. So let's dive in with some examples. Here we have the double integral over R of x e to the xy. Now, x e to the xy is a perfectly continuous function, so we can, in theory, integrate in either order that we like. But let's think about it. If we decide that we first want to integrate with respect to x, because we'll be viewing x as a variable and y as a constant, we're essentially integrating x e to the x. And if you remember from your Calc 2 days, in order to integrate x e to the x, we have to use the technique of integration by parts. Now there's nothing wrong with integration by parts, but let's see what happens if we try integration with respect to y first instead. So here's what it would look like. Suppose we want to integrate first with respect to y to avoid integration by parts. Since x is just a constant and y is the only variable that matters, we're integrating e to the xy, and that requires u-substitution. So we would let u be what's in the exponent, the xy. When we take our derivative for du, notice that we're still focusing on y as our variable and treating x as a constant. So du in this case would be x dy. Our double integral then looks like this. So e to the xy became e to the u, x dy became du. I kept my original inner bounds y from 1 to 2, and then we let the outer integral from 0 to 1 of dx just tag along. Okay, so now we're integrating e to the u, which is of course e to the u. Since u is xy, that inner integral will integrate to e to the xy, and we'll evaluate y from 1 to 2. So we get the integral from 0 to 1 of e to the 2x minus e to the x. Integrating with respect to x, we get 1/2 e to the 2x minus e to the x, evaluating x from 0 to 1. So 1/2 e squared minus e, and then minus 1/2 minus 1. So our final answer is 1/2 e squared minus e plus 1/2. Great. So had we integrated first with respect to x, we would have had to use integration by parts. Since we chose instead to integrate first with respect to y, we were able to get by with the simple u-substitution. Let's look at another example. Here we want to evaluate the double integral over R of xy cosine of x squared y. A nice continuous function. Fubini says we should get the same answer regardless of our order of integration. Think for a minute about which order you would like to try. Observe that if we decide to integrate first with respect to y, then focusing only on the y as the variable, we will be integrating y cosine of y. And that requires integration by parts. So let's try integration with respect to x first instead. If we integrate first with respect to x, then we're integrating essentially x cosine of x squared. And that requires u-substitution. So we will let u be that inside function, x squared y, Since everything is with respect to x, when we take the derivative, it will be with respect to x. So du will be 2xy dx. Or we can rewrite this to say that 1/2 du is xy dx. So our double integral looks like this. The cosine of x squared y becomes the cosine of u. And xy dx becomes 1/2 du. We kept our original inner bounds, x ranging from 0 to 1, and then our outer integral from 0 to pi over 2 of dy just tags along. Okay, so in that inner integral, the integral of cosine of u is sine of u, where u is x squared y. We evaluate x from 0 to 1 to get 1/2 times the integral from 0 to pi over 2 of the sine of y minus 0. The integral of sine of y is negative cosine of y with the 1/2 tagging along, and we evaluate y from 0 to pi over 2. So our final answer is 1/2. Great. Again, had we integrated with respect to y first, we would have needed integration by parts. But by integrating with respect to x first, we were able to get by with the simple u-substitution. Let's do one final example. Here we have the double integral over r of 2y plus 3xy squared, all divided by 1 plus x squared. Think for a minute which variable you want to integrate with respect to first. Well, if we choose to first integrate with respect to y, then that denominator of 1 plus x squared is just a constant. So we can even kind of pull it off to the side and know that it's just going to tag along. So let's do that. So if we integrate with respect to y, we'll have 1 over 1 plus x squared tagging along, and the integral of 2y plus 3xy squared becomes y squared plus xy cubed. We evaluate y from -1 to +1, and don't forget that that outer integral has to just tag along until we're ready for it. Evaluating, we'll have 1 over 1 plus x squared times 1 plus x minus 1 minus x. So we end up with the integral from 0 to 1 of 2x over 1 plus x squared. This is a nice Calc 2 integral. We can do a u-substitution. Let u be 1 plus x squared, then du is 2x dx, and so our integral becomes the integral of 1 over u du. So we get the natural log of 1 plus x squared from 0 to 1. So our final answer is the natural log of 2. Great. Now I'd like to point out that had you chosen to integrate with respect to x first, that would have been just fine. The trick, if you want to integrate with respect to x first, is to split the numerator. So the 2y over 1 plus x squared with respect to x, you'll use your arctangent function. And then for the 3xy squared over 1 plus x squared, you'll do the same u-substitution where u is 1 plus x squared and a natural log will come into the mix. So if you're feeling adventurous, you can try it in that order as well to confirm that you get the exact same answer of natural log of 2. That's all for now. Thanks, guys. Bye.